I'm live streaming this to YouTube because it's got to be up there for someone. And
why are you recording things, you creepy Jew?
So I can farm the views.
What views? I've seen your YouTube channel.
Okay, I know you've.
The most popular video is you playing with Legos.
Yes, I know. And that wasn't even me playing with Legos. That was me recording my friend playing with Legos.
Oh. Let me clean that up.
That's.
I've missed you though, Judah.
Hello.
Why do you avoid me?
I don't. I'm just never in the same place as you on accident.
We should go back to sparring again.
You should come back on the mats.
Trust me, I wish I could. Why are you still recording?
Because I'm live streaming this for Reddit.
For what? Nothing's happening yet.
There's a subreddit for AP Chemistry. It's not very active, but I was like, I'm gonna live stream this so that since it's not a secure document, but it's not really up online anywhere.
Hey, so, FYI, ladies and gentlemen, everything you're going to be watching, it's going to be a video of it on the actual TVs. So, if you normally cannot see the TVs or the screen from the back of the room,
That's not mine.
you're going to want to be in the front of the room.
I don't know whose it is.
And I would,
It was
a
just
couple
in
of
here.
things, I would recommend having a highlighter and a pencil out so that you can make some notations and notes on these scoring guidelines. Because if you're not writing anything on them down, on them, why are you here?
So we can write on them.
Oh yes, those are yours to keep.
Alright, thanks. Okay, let's do
I don't
this.
need 30 copies of them. Yeah, they are yours.
There's an AP Chemistry subreddit.
Of course there is.
Yeah. There's like 2 actually. Neither of them are very active.
Well, imagine that.
Just a couple more minutes for stragglers, and then we're gonna get started. So they can just miss the first couple minutes. There.
You know it's over there, right?
I thought it was on that one too.
No idea. He said the actual TVs, so that's gonna be over there.
What do you think?
Alright, I am gonna turn the lights on the back. Hey, I will turn the smartboard on too.
Oh, okay.
Thank you, sir.
I just wanted it to be dark enough that you could actually see it. For sopping up spills. Thank you. Yeah, whatever. Hater.
I miss the VHS.
Hello, everyone.
Alright, I'm
Welcome
gonna
to
skip to
tonight's
the beginning of this,
We're
because
all on
to be honest, hey, so kind of giving everybody a heads up, this is not a video that was put together for students. Okay, this is put together by, well, for the American Association of Chemistry Teachers. So it was for chemistry teachers, and the man who is going over this, he is the chief reader for the AP Chem exam. And this is every bit of the information that they pretty much tabulated after grading last year's AP exam when they graded it in June. Okay, because they actually grade them in June. And so he's going to go through a few things at the very beginning, just kind of about the exam. Then, after a little bit, he'll start going through every single question. And that's why I gave you the scoring guidelines, so that you actually had the entire test and what the scoring guidelines were. But to get the most out of this, you should be writing stuff down on every one of these questions as far as what he is saying, what would have also gotten credit, what the big student mistakes are, that's key, and how not to avoid, or how to avoid them.
How to not avoid them.
So please, hey, please, 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 keep the talking to a minimum so that way your classmates can hear. They don't care about hearing your conversation, they care about hearing this. That's why you're all here.
I am chief reader of the AP Chemistry program, which means that I oversee the scoring of the exam, the physical reading site, and I also am one of the members of the committee that writes the exams. I'll talk a little bit in the future about how that gets put together, but I know that mostly you're probably interested in talking about the 2017 exam itself, so I'll skip right there. We are going to talk about some of the logistics that go into the beginning of the exam, how it's written, how it's scored. You may know some of these things already, so I won't spend as much time on that unless you want me to talk more about any one of these particular bullet points. But I'd really like to get to the end of these, talking about score profiles, general advice, and some of the common errors, misconceptions that we saw on the various questions of the 2017 exam. I took all these photos in Salt Lake City, by the way, at the reading, so you'll get to see some of my photography along here. Writing the exam is performed by the development committee. It's a blend of high school and higher ed teachers. They're fantastic people to work with. We also work closely with ETS and the College Board, as you would imagine. When we're writing the exam, you're probably familiar with the big ideas, the enduring understanding, the learning objectives, and so forth. These are the structure of the AP Chemistry curriculum. Correspondingly, every question that we write on the AP Chemistry exam is going to be directed to a specific learning objective and use at least one of the science practices that's outlined in the course exam description. So when we're writing these free response questions, we have certain goals in mind. Certainly we want to target the knowledge and skill that's within the curriculum. We want to address specific learning objectives, use those science practices. With the redesign of the 2014 exam, we're interested in probing conceptual understanding more than just turning the crank and out comes a number on your calculator, kind of algorithmic problem solving, but math is still alive and well. We want to make sure that chemistry is realistic, of course, that the exam is writable by a student and scoreable by us. That's really important. We also want to involve a range of different challenge levels, and some questions are going to be more challenging or less challenging, but we do want to make every single part individually accessible while we're still differentiating levels of student ability. In terms of what a student or a teacher would see, they see two sections with various numbers of questions on them. Section 1 is multiple choice. Section 2 is free response. The free response structure is stable, meaning that the first 3 questions are always called long questions. Those are each worth 10 points. And then there are 4 questions afterwards. You call those the short questions. Those are always going to be worth 4 points. And that structure is going to be stable. So what the AP readers see when they show up to Salt Lake City is a long
That's why I said, you don't want, in case you're the last one they grade at the end of the day, it literally is hundreds.
We do get it done. The operational volume is large. It is still climbing. It looks a little bit like a titration curve. The rate isn't quite constant, but we had 150,000 exams in various forms that we scored at the 2017 reading in Salt Lake City. The way that students earn points, first of all, they have to follow directions. Showing work is really important because without that, we can't see evidence of understanding. Often we can't award credit. Also, paying attention to significant figures is always going to be something important for students to do. One thing that not everybody knows is that every part of every question is broken down into 1-point pieces. So everything that we read, we're essentially scoring binary. Every scoreable element that we've identified on the scoring rubric either earns a point or it doesn't earn a point. And we add points in. We add together points earned. We don't take points away or subtract points for things that get missed. Students absolutely have to show their work, and each part is independently scoreable. If things kind of go off the rails in A and a student makes an error in part A, they're not going to be held in double jeopardy on parts B, C, and D if they have to use that previous answer. We acknowledge that the student has only made one error, and we do try to follow their work through on subsequent parts of the exam. We often have one question that we'll designate as the significant figure question. That one kind of stood out in the 2017 exam where it's very explicit, and that answer is going to require, in order to earn credit, that the student uses the correct number of significant figures. And then, of course, we want to be consistent, we want to be fair, we want to be accurate. So ideally, any paper read by anybody at any time in the reading should always result in the same score. We have some structures in place in the reading that do this. We have pre-reading where we look at student samples, we look at actual student papers, we finalize the scoring rubric. As we implement that rubric, we have pre-reading where there's some training of the readers and folks get on board. We do try, it's critically important that we're clear in how we're scoring as we communicate with those who are reading and scoring the exams. We talk about consistency. We have a series of training papers. There's a series of oversight and I'll call it quality control, dealing with continuous retraining, back reading. There's a table leader who will have responsibility for a group of readers, and those readers' scores are being checked by a table leader. So there's always some form of quality control conversation between leaders and readers. And there are stats on every reader that help us to identify if somebody's being overly stringent or overly lenient. Lest I forget, being an AP reader is a ton of fun. It's how I got my start. I owe somebody a credit for the artwork here. But the next reading is in Salt Lake City once again during the first week of June. You get to do a lot of things that are both professional development, intellectual growth, growing as a teacher. There's a lot of fun involved too. It feels a little bit like summer camp. Number 5 is important. They feed us very, very well. It's a terrific experience. There's some information here on how you could apply to become a reader. There's an online application process depending if you're higher ed versus high school teacher. But you can follow these links and you can submit an application, and ultimately you will go into the queue to learn how to become a reader.
You have to be a high school teacher first.
Yes.
We have a quick question. How many different readers are scoring each question?
It depends on the question. The long questions that are worth 10 points might have 20, 40 or so readers on them. The short questions are quite a bit smaller. They might have 5, 10, 15. And we do make mid-course corrections a few days into the reading where if a particular question is reading especially slow or especially fast, we will sometimes reassign readers. But we start with a pretty even distribution where the long ones maybe get 40 or so, and the short ones get smaller question, smaller number of readers there, proportional to the speed that we think they can read. So when looking at the 2017 exam, we would really hope that if you look at how many students are scoring each total raw score, at 1 through 5, we would hope for something like this. Of course, maybe you really expect something like that, but we really see, by the way, this is not real data, something kind of a blobby like that. But there are breakpoints along the way, and that's how statistically the 1, 2, 3, 4, 5 AP overall scores are actually set. Having consulted with the College Board, ETS, I'm in on the phone call, the chief reader's in on the phone call, statisticians, and they work out where those breakpoints are. So there's a conference call, we look at the raw scores. We have a set of questions in the multiple choice section that occur every year, and they statistically equate students' performance as a group on one year's exam to previous years. So that helps us to figure out differences in the exam versus differences in student ability from one year to the next. And it also helps us to ensure that long-term consistency, that a particular score in any given year holds the same meaning. So looking at the 2017 exam, question 1 really went great, looking at those average scores. Questions 2 and 3, maybe less so. Questions 4 and 5, kind of right in the middle there. We usually want to group students pretty close to the middle. Question 6 was a little bit weaker, but then we bounced back again on 7. So in total, out of the total number of scoreable elements, there were 46. The average score was just about 17 and a half. When you look at the distribution of scores on the 2017 exam, you'll notice there are just a smidge fewer 5s this year in 2017 as compared to the previous year, but there's more 4s. And that will happen based on the performance on those questions that statistically equate student performance from one year to another. And the statistical analysis this year showed that as a group, the 2017 test takers were slightly less capable, but not by much, compared to the comparable group last year. So we didn't quite have as many 4s, didn't have as many 5s, but we did have more 4s. Big picture advice, I talked to a lot of people. I talked to teachers, I talked to people scoring the exam, I talked to the leadership at the exam. They have some big picture advice. One piece of advice to pay attention to is just to follow the directions, to do what the question asks you to do. Read the question and answer what the question is actually asking. It's like prepping a lawyer prepping a witness, where just answer the question.
Sound familiar?
You don't have to say a whole lot.
Not at all, sir.
Yeah, I think you've heard this a few times. Answer the questions asked.
To show all the work that they do, show the units throughout the calculation, not just left on the end. And that the rounding can sometimes be a little bit funny if you do that intermediate. You should only do that at the end. And of course, pay attention to the
Did you catch that at the bottom of the
in terms
screen?
of chemical intuition, that check
for a
of the
second.
final answer is always important. And right to pay attention to is just to follow the directions, to do what the question asks you to do. Read the question and answer what the question is actually asking. It's like prepping a lawyer prepping a witness, where just answer the question. You don't have to say a whole lot necessarily. I think as teachers, it's always...
All right, so look at that. On here, I'm going to be real quick about this. I'm not going to stop him very often because this is long enough as it is. But everything that's on this slide, you've heard come out of my mouth 100 times. Answer the question that is asked, not what you wish it had said. This is the head reader. He's one of the ones who writes the damn test. Answer the question that is asked. Number 2, show all your work in the calculations. Show all your units in the calculations, throughout the calculations, not just at the end. And then the last thing, do all your rounding at the end and keep track of sig figs. Okay, so I just want you to be aware that that is not just me saying all this stuff because I want to be hard on you. We're all hard on the students, and this is why. Okay, continue on. Maybe.
It's important that we encourage our students to show all the work that they do, show the units throughout the calculation, not just left on at the end. And that the rounding can sometimes be a little bit funny if you do that intermediate. You should only do that at the end. And of course, pay attention to significant figures. In terms of chemical intuition, that gut check of the final answer is always important. And we will always see on the AP exams these particle level diagrams of molecules or atoms or interactions, and helping to explain. What we always tend to do as chemists is try to figure out what's happening at the atom or the molecular level and try to explain how that's manifested in the world that we can actually observe in the macro scale. So in the laboratory, we always encourage our students to think about what's happening to the atoms, what's happening to the molecules, what's the theory, ask error analysis, what if this were to happen, or the students build something, or this were too high or too low, or contaminated, and so forth. And that gives students that development in chemical intuition. Making claims and providing evidence really is the bread and butter of the AP chemistry exams and free response questions, helping students use the correct vocabulary. Ions are not the same as atoms, are not the same as molecules, and so forth. Simple sentence structure. We've declared war on pronouns. Talking about it and that can be very confusing sometimes. And differentiating what really constitutes a true explanation versus just reciting something. Here's an example here about atomic size. Position on the periodic table isn't an explanation. It's related to the explanation. And then an error analysis in a laboratory setting, for example, helping students to follow through from what error occurred to what would the actual outcome be, how would this error impact the outcome, is always critically important. Graphical information shows up quite a bit in various parts of the exam. Those particular level representations are there. Lewis dot structures will always be there. They're never going away. Balanced net ionic equations, there's usually at least 1 point per year per exam, something dealing with net ionic equations. And then there are lots of graphical information and tabular information that helps students to interpret the text. So that's the big picture. What I'd like to do now, and if I sped through that and you still have questions, I'd be glad to answer those, but I figured you would be here for the main event, which is talking about the exam itself. So on question 1, we're looking at the synthesis of carbon tetrachloride. The clustering of students here around 6 points out of 10 is actually quite good. So we have a question here where carbon tetrachloride is being synthesized in the gas phase from these gaseous reactants. The first question asks how many moles of Cl2 are in the container. This is one of those questions where a student ought to be able to respond fairly quickly and accurately using the ideal gas law. So this was a 1-point question, and sometimes the algebra got turned upside down or mixed up a little bit. Some students didn't need to convert let's see, they started out with Celsius and then they misconverted to Kelvin or didn't convert to Kelvin at all. They did some interesting things with the volume sometimes. Sometimes they incorrectly assumed STP and used that 22.4 liters per mole. We see that a lot.
This is going to be
likewise, there are multiple values of R depending on the
What's the
unit.
common errors down here?
One reason why it's important to look at units.
Pay attention to those, because you guys make a lot of those.
Follow-up question is
You're on number 1.
Geometry question about how many grams of product could be, how many grams of reactants would be required to react completely with the available Cl2 gas. So there's that key 1 to 3 molar ratio that's important. That is 1 point awarded for recognizing that, and then 1 point for having the correct mass. This calculation is pretty straightforward, but students didn't always show their work. We saw that sometimes the students would start with an incorrect number of moles of Cl2 or incorrect molar mass of CS2, but by far that error of the 1-to-1 versus 3-to-1 versus 1 to 3 molar ratio was probably by far the most common mistake that we made. And if you write down moles of Cl2, moles of CS2, include those labels throughout the calculation, the dimensional analysis can really help students out. We then have a situation here in question 1 where the student sees that the reaction is thermodynamically favorable, however no reaction occurs at an appreciable rate. But when the temperature is raised, then the reaction does proceed. So what the students see here is first they're asked to explain why it is or how a higher temperature can impact collisions and therefore cause the reaction to occur. So we were hoping that students would say something about increased average kinetic energy at the start of the at the higher temperature. We were hoping that students would talk about intermolecular collisions that are increasingly effective or have sufficient energy, overcoming activation barriers. Unfortunately, some students here didn't quite answer the question. They told us some things about activation energy without really saying anything about collisions or tying that to this particular situation that they see in the question. They need to say not just that there is a greater number of collisions, but they need to talk about what those collisions mean, or a greater number of collisions that are effective, i.e. leading to an actual reaction. Sometimes more than a few students said, well, actually, the reaction actually is unfavorable, right? They change the value of delta G or they contradict the prompt. But by and large, we very frequently saw temperature as being a catalyst, right? The heat is a catalyst that either lowers the activation barrier, reasoning along those lines.
Hey, Paul?
Yes.
We have a quick question. Is there any preference as to where molar mass is rounded?
We usually see 2 decimals out. I think, you know, over rounding can be a little dangerous, but we do build in a little bit of wiggle room in our scoring. If a student were to drop one of the decimals or round a little bit, that's usually okay. It's not a test in calculating molar mass.
Great, thank you.
You're welcome. Thanks for the question. And then the students have a graphical description of what's going on with the fraction of collisions, the energies of the collisions at low temperature and high temperature. They're provided with the profile at high temperature, and they're asked to draw in the profile at low temperature. And we would hope that the students would draw a curve that shows a peak that is to the left, that the peak is to the left of the original curve, and also that once we reach down by the activation energy here, I can point out that this curve is lower at the activation energy than that one there. Unfortunately, some students drew the curve that they drop below the x-axis, the negative fraction of collisions, but very commonly what we saw was that they just redrew the solid curve and just drew it lower than the original one, or they would change what the activation energy is. The activation energy is different at various temperatures in this situation.
I would be writing down these misconceptions, though, ladies.
Can we change gears a little bit, talk
We're
about
wrong.
F2CL2?
Because
This is a Lewis dot structure question, so the students are provided with the molecular framework. They're given these atoms, and they're asked to draw the Lewis electron dot structure. There was a temptation to add valence electrons, remove valence electrons. Having that accurate count is really important. Following the octet rule will always be important. And the students are specifically prompted to draw in the electron pairs, so that's something we really will be looking for. There's a temptation as well to draw a lot of single, double, triple bonds, multiple pi bonds in the system when it's not necessary, given the number of valence electrons that we have. So based on the structure, the students are then asked to approximate the bond angle between the chlorine, the sulfur, and the sulfur. So we're talking about this bond angle right here. We accept it numerically. Most students would say 109.5, indicating the recognition of sp3 hybridization. We would take numbers just ever so slightly higher at 110. We want to make sure students aren't confusing that with sp2 hybridization. We would take numbers a little bit lower too. The really savvy students would say, oh, this kind of reminds me of water. The bond angle in water is about 105. It's, you know, almost tetrahedral-ish, but it's ever so slightly smaller. So numerically, we took any answer between those two numbers. If you want to know the real number, according to this paper, it's 108.2. So that's slightly smaller than 109.5, like we would expect. A lot of students would say, well, my Lewis structure is drawn in a straight line, so the bond angle must be 180 degrees. It's important to emphasize the difference between a Lewis structure depiction and the actual three-dimensional geometry. Sometimes students wouldn't count electron domains correctly, or they would say the bond angle is tetrahedral, and unfortunately tetrahedral is not a number.
Hey, Paul?
Yes.
Another question is related to the graph before. It says, how does the scoring of the Maxwell-Boltzmann distribution question go? Did the detail of being worth 2 points cause difficulties in scoring?
The fact that we made it worth 2 points actually benefited the students. If it were only worth 1 point, very few students earned 2 points on this question. Most students earned 1. Very few earned 0. We had an original structure in place that this had only been worth 1 point, almost every student would be earning a 0 because it wasn't perfect. So we decided to look for the two parts. Most students got this bottom curve here being below the activation energy. That was the point that they earned most often. Our goal is to be fair. Our goal is to try to help the students and ultimately to differentiate. And we were pretty successful. It would be unfortunate if we had a lot of zeros and a lot of twos and not many ones. Students were kind of clustered in the middle on that particular question.
And then one more about the bond angle. Is it okay to say less than 109.5?
That would earn credit. The scorers disregarded any kind of qualifying terms like, slightly bigger than, or they just looked at the actual number that the student wrote. So that would be acceptable for credit.
Great, thanks.
You're welcome. Carbon tetrachloride can also be produced using this other reaction, and this one happens to have HCl as a byproduct. So the students have to identify the types of intermolecular forces that are present in HCl. And the temptation is to write hydrogen bonding. However, hydrogen chloride is not one of those cases. A lot of students omitted London dispersion forces or said something about van der Waals forces, and this is something we have to be vigilant about because different textbooks define van der Waals in different ways. As a matter of fact, when I learned that van der Waals was synonymous with London dispersion, but if you dig deep and look at what the IUPAC has to say, van der Waals is actually a blanket term that is an umbrella that covers all intermolecular forces. So it's important to talk about London dispersion forces specifically. A lot of students talked about the type of bond between hydrogen and chlorine. In other words, confusing an intramolecular interaction with an intermolecular force. What's going on inside the molecule versus what's going on among neighbors between molecules. And then the students get some data about carbon tetrachloride and HCl. And at the reduced temperature, the carbon tetrachloride condenses to a liquid, HCl remains as a gas, and the students asked to justify that observation. So we would hope that we would see students saying something, well, the boiling point, or in this case the condensation point, is a proxy for the strength of the intermolecular forces. And it's interesting in this case because the outcome is actually contrary to the trend that one might expect, where you think, well, dipole-dipole forces, those are always stronger than London dispersion, aren't they? And the answer is, well, not always. The students do need to make specific reference to the data, would sometimes make an argument that's contradictory to the observation that was stated in the prompt. There's a little confusion about higher boiling point, lower boiling point, what does that mean? And also comparing London dispersion forces not to polarizability or the size of the electron clouds, number of electrons, but just talking about, well, which atoms are heavier.
Hey, Paul, there's a quick question about nomenclature. Can a student write LDF instead of writing out London dispersion force?
Absolutely. We see LDF all the time. LDF is one type of INF, right? That's an intermolecular force. The readership is very familiar with the common abbreviations. We don't have any problem with that. You should make sure that the abbreviations that you use are standard or common and not just unique three-letter abbreviations that you happen to invent on your own. We do need to understand what the student means. So the big picture here is helping students to practice skills, practicing algebra, using significant figures and rounding and using units in their work, reminding students to read carefully, respond to the actual question. But I think maybe more interesting and more meaningful for the students is having them describe in their own words what happened when a temperature is elevated or reduced, or having them describe in their own words correlations between boiling point and strength. As we all know, that's one of the hardest things to get students to articulate clearly, but it's also one of the most important. Talking now about fulminic and isocyanic acid, this is question 2. We have an equilibrium between these two very similar species, and unfortunately, most students are kind of clustered at the lower end of the score here. The average is only 3. 3.15 out of a possible 10. So the first question provides the students with two Lewis dot structures, and they are resonance structures, although that word isn't quite used here, but that's what they are. And the student has asked, well, which of these two Lewis structures is better? This is a question about formal charge, and this was a 2-point. They get 1 point for correctly assigning the formal charges, and then a second point for a correct explanation. The nitrogen atom has a positive charge in each of those two structures, although we have to then look at the negative charge being on oxygen on the left-hand structure versus negative charge on the carbon on the right-hand structure. And we would hope the student would say something about the greater stability of negative charge on the electronegative oxygen on the left. Formal charges are in scope. They're part of the course. We don't always see it a lot, but it is in there. And it's also important when students are asked to make a comparison that they talk about both structures, that they actually have to compare one to the other rather than focusing in their explanation just on one of the two structures. More of a skill in rhetoric, I suppose. So the students have this interconversion between these two forms of these two isomers, and they get some thermodynamic data about the bond enthalpy of various bonds that are found in these two structures. And they're asked to determine the delta H naught for this process. So the students can use this data then to sum up the bond association enthalpies of all the bonds that are broken and the enthalpies of all the bonds that are formed. They get 1 point for having the correct mathematical form of this equation, and then a second point for calculating correctly. This can be a little hairy sometimes because there's quite a bit of arithmetic, and following that negative sign through can sometimes be a little tricky. Predictably, students would sometimes reverse the equation. Is it bond association enthalpy of bonds broken minus formed, or is it formed minus broken? I've been talking with this about teachers. You can intuit your way through that because you think, oh, does it take energy? Is it a negative delta H or a positive delta H to break a bond? Is it a negative delta H or a positive delta H to form a bond? So there are a few errors in transcription, but mostly arithmetic, just a large number of digits here to keep track of, and sometimes didn't quite work out, but they would get the first point for the setup. The students presented with the claim that the delta S for the reaction actually affects, that the delta S for the reaction is 0, and they're told that the student's claim is correct or accurate, and the student is asked to indicate why. We would hope students would say something like, well, both reactants are gas phase, there's one molecule of gas on the left, one molecule of gas on the right, that there's no change in the physical phase, numbers of molecules. It's just a rearrangement of atoms. When students didn't earn the point, it was often because the students would say, well, the two molecules have the same molecular formula, or the structures are very similar, and they really need to say a little bit more about what is the connection to a prediction about delta S. So keeping those previous results up in the upper left corner there, the student is then asked which of these two species, the reactant or the product, is present in higher concentration at equilibrium. So the student has to use a justification in terms of thermodynamic favorability, i.e. delta G, and looking at the equilibrium constant. If the student follows the chain of logic that if delta S naught is close to 0, then delta G naught is approximately the same as delta H naught. Therefore, we can get a calculated value for delta G naught, and that's a highly negative value. That must mean that the equilibrium constant is greater than 1, and that indicates that the products are favored at equilibrium. So the students need to make a correct choice. That's one point, because the question does ask which species is present in higher concentration. The student actually has to make a choice. Sometimes the students didn't make a choice at all. They would start calculating and using equations without actually answering the question. A lot of times the students would make up a value for delta S naught or not go back to that previous result. or they wouldn't make specific reference enough to K. And when you read the question, they're prompted not just to justify in terms of thermodynamic favorability, but also to look at the equilibrium constant as well. So there really has to be some kind of reference to K there. It could be mathematical, it could be qualitative. We accepted both of those lines of reasoning. The decomposition of a related product here is shown here both in tabular form as well as graphical form. If this looks like a kinetics question, that's because it is. So the student proposes a rate law for this decomposition reaction. And the first prompt is for the student to explain how the data supports this proposed rate law. It's proposed to be first order. There are a few ways to do this. I think the easiest way is to inspect either the table or the plot and see that the half-life of the reaction does not change. It's constant at all points throughout the reaction, and that's a property that's characteristic only of first-order reactions. Some students did it in slightly more convoluted and difficult ways, but they were equally successful. There were some common errors that said, well, the fact that the reactant disappears, that means the reaction's first order, or the reaction has a half-life. A half-life exists for this reaction, therefore it's first order. Or that, well, the exponent is 1 in the rate law the student proposed, so it must be 1. Or there's just one reactant, so it must be first order. The tricky one was point 4 here about the linear plots. Some students actually went through the trouble of calculating the natural log of concentration of the reactant, and a lot would draw in those numbers here. And if they could show us clearly enough that that plot really was linear and show us numerically or graphically, they would earn credit. But by and large, students who tried to go down this path just made an assertion without any supporting evidence or data to substantiate their claim. They just said, well, you know, if you were to plot the natural log of this concentration, you'd see that it was first order if you plot that versus time. We had a lot of discussion about that one. We finally came down to the side of what kind of evidence has a student shown, rather than just memorizing what is a fact that is true about first order reactions versus how is the student actually making use of the data to show us that it's true. So the students are then asked to determine the value of the rate constant. There's two ways. The one we call the easy way, using the equation off the equation sheet, and the other we call the slightly harder way, still using data from the table. Both are equally correct. You arrive at the same answer either way. The important part here is that the last sentence, to include units with the answer, was critically important. A lot of times the units were simply completely missing, and the students are specifically prompted to include units. Quite a few students calculated a negative value of a rate constant as well. And that kind of goes back to the gut check we were talking about earlier. Can such a thing be possible? And finally, the student is asked to design an experiment where the reactions run first at a pH of 13, and then the student has to describe what they would do what would they change in the experiment to determine if the rate of reaction also depends on the concentration of hydroxide. And the student would earn credit for something as simple as repeating the experiment at a different hydroxide ion concentration and measuring how the rate or the concentration of the reactant changes with time. Unfortunately, students would sometimes try to change too much at once. If you raise the temperature and change the hydroxide ion concentration, for example, or changing the hydroxide ion but maintaining identical pH, which is a contradiction, or just the fact that the student said they would measure the pH. It really has to do with making an experimental change to the setup of the experiment, something fundamentally about the design, and then that observation or the measurement. So there's two parts. There's a part here about a different hydroxide ion concentration, and then there's here about the observation of what the student is actually measuring.
Okay, Paul, we have a quick question about the units for K. It said, what was the rationale behind not applying a separate point for the rate constant unit? Many questions in the past have done this.
Yeah, and it depends. That's a fair point. And it really depends ultimately on the samples that we read during the pre-reading. If we had assigned it as a 2-point question, and it looks like either everybody's earning that point or nobody's earning that point, sometimes we'll make changes. This was, we thought, a simple enough question that it would be worth 1 point. A student could just reach for the equation sheet, crank out a number, so we wanted to add a little more layer of complexity there. Otherwise, we had 1 point for using the equation sheet correctly, and then 1 point for writing the letter H and -1. And we came down on the side of making that only worth 1 point.
Yeah, ladies and gentlemen, hey, the H on that one is for hours, because that's what the rate was in. That was the time on it. So you can just abbreviate.
The advice from the leadership on this particular question is keeping in mind that formal charges are alive and well, and that they're important to know.
Your rate.
Having students estimate delta H of reaction on association enthalpies is computationally straightforward. And again, remembering the mathematical form and how you use it is something that relies on intuition and practice. Referring to data when analyzing kinetics or any form of data, using the table, using the graph, that's always important. Keeping track of the units in the calculation, and proposing an experiment or redesigning an experiment or coming up with some change to an experimental method. As always, it's a higher order kind of question, but it's an important kind to ask, because it helps the student to see how it is that scientists think and how scientists work. The last of the long questions dealt with NO and HNO2, and once again, the student scores on this one averaged a bit on the lower side than we would have liked. They're presented with an equilibrium reaction, N2 gas reacting with O2 gas, and they're asked to write the equilibrium expression, Kp, for this reaction. So if you look at the species and their stoichiometric coefficients, we'd like to see something like this. Sometimes students would write brackets around the NO2. That actually still earned the point. It's a rigid container, the volume doesn't change, so technically the partial pressure and the concentrations, while not identical in meaning, the relative ratios of those two still tracks. So difference between a KC versus a KP is an important point to make from the standpoint of teaching. Although on the scoring on this particular part, student gave an answer like that, they still earn credit. And then the students have a situation, initial conditions of the two reactants, and then some conditions leading to the final outcome at equilibrium. I don't know if ice is a verb, but a lot of teachers I know will say, oh, you need to ice that. I say, what? No, you draw a table. It's important to keep in mind that there's that factor of 2 in the formation of NO as compared to the disappearance of N2 and O2. This was a 2-point question, and students earned 1 point for getting the correct concentrations, the equilibrium concentrations of the species, and then 1 point for the correct calculation based on the concentrations that they determined. A lot of students would use the initial pressures of the reactants, and they would try to put 0 into the expression they had just written, and it never didn't end well. Missing that 1 to 2 stoichiometric ratio was quite common. And keeping in mind, what does that 0.122 atmospheres mean? Is that equal to X, or is that equal to 2X? That missing factor of 2 was quite common in this question. So nitrogen monoxide can also react to produce an acid. This one is HNO2, and here is our favorite topic of buffers. So the student is asked to explain using a net ionic equation for the reactions between an acid and a base. In other words, when the student has a solution of HNO2 and they add sodium hydroxide, what is happening to the species, and how do you reduce that down to the net ionic equation? The student is also asked to use this net ionic equation as part of the explanation for how or why the reaction between this particular acid and base can lead to a buffer solution. So if the student recognizes that the situation creates a mixture of a weak acid and its conjugate base, that was sufficient for credit. Unfortunately, HNO2 looks an awful lot like nitric acid, so a lot of students said that it was just a source of H+. Didn't recognize HNO2 as a weak acid. If you read carefully, students do get indication here that this really is a weak acid and not a strong acid. And they talked about the formation of water, and water is a buffer, or misidentifying some of the components, talking about only the acid or missing the base and things like that. And one of the buffers continues. Now we have a volume that students are asked about that the student should add to a sample of HNO2 solution to make a buffer solution with a target pH. And students approach this question one of two ways typically when they were successful. Either they'll say, well, I've added half enough acid that gets me halfway to the equivalence point. Also sometimes use the Henderson-Hasselbalch equation that would get them to the same answer. In this case, the pKa of the weak acid is 3.4. That matches the target pH of the solution the student is trying to create. This is a 2-pointer, 1 point for the correct volume, and second for indicating either mathematically or in words that they were equal concentrations of the weak acid and its conjugate base. Students do love the equation N1V1. They use it almost all the time for almost every question. Unfortunately, in this case, that doesn't lead to a half neutralization of the weak acid. It leads to a complete neutralization of the weak acid. So the students do need to think through what that equation does well and when it's appropriate, and when it might be more appropriate to think about other problem-solving strategies. And lastly, this is the last we have to do with buffers tonight. Talking about the student making a buffer solution, a second student making a different solution with the same buffer, but with an increased amount of, sodium nitrite. And the student is asked which of the two buffers, the first buffer or the second student, is going to be more resistant to changes in pH. The best answer said something containing the term buffer capacity, although students were in the minority who actually did that. They didn't have to use that exact term, but if we could understand the students were talking about either there's a greater amount of there's a greater amount of acid and base, or something about a resistance to pH because there's more of that reactant to react with. That led to a wording of the point there. Students didn't have to use the words buffer capacity, but we did have to recognize that concept being there somehow in its foundation. And sometimes students didn't realize that the two buffers, even though the amounts of the components are different, or the concentrations of the components are different, that the two buffers still have the same pH. So students are making arguments about the initial pH of the two buffer solutions being different. And then our particle level diagram. So a new buffer is made. I lied. This is the last buffer question. So we have this particulate level diagram that shows the acid molecule and the conjugate base ions here. And if you count off, there is a greater number of these molecules, of the acid molecules inside the box as compared to the NO2 minus ions. So the student is asked, what is the pH of this buffer in comparison to the pKa of the acid, or the pH at that half equivalence point? And hopefully students could either count particles and make a qualitative statement, or use more mathematical reasoning and talk about log and the log term and the Henderson-Hasselbalch equation. Either way, students could be successful if they were correct in interpreting this particle level diagram. This is another question that gives the students a choice, right? Greater than, less than, or equal to, and then a justification. And very often, questions that are constructed this way are often going to be worth 2 points, one for the choice and one for the justification. although there are some cases where the two are bundled together at one point, depending on the complexity of the question. It is important that the students realize that we are looking at proportionality here. In other words, these particular level diagrams are representative of some kind of physical reality with the particles.
So count them.
The advice from our leaders and readers is thinking more deeply about the difference between KP versus KC, helping students to practice setting up those equilibrium ice tables. At first, with one-to-one stoichiometry is usually the best way to learn it, but then with these other cases where the stoichiometry between reactants or reactants and products isn't always one-to-one, it could be 1 to 2 or 1 to 3. If you practice using those different stoichiometric factors. And then there's our good friend buffers, right? That seems to be the perennial struggle for many students. What is the definition of a buffer? What are the different ways that a buffer could be prepared? There are 3 different ways to do it. And then lastly, thinking about those particular level representations and having students connect that cartoonish diagram to a physical reality in the laboratory. We're on to the short questions now. Here's our friend chromatography. I talked with a lot of high school teachers over the summer, and it seems like many of them do perform this experiment. However, the student performance is lower than we might have liked or expected on this particular question. The mode in this one was a 1 point out of 4. So the situation is this. A student has 3 different dyes that are developed on a TLC plate, and then the student does a separate experiment with an unknown dye that is either A or B or C, and then has to identify what it is based upon the results of that chromatography experiment. One of the key factors here is that the solvent front has not risen at equal height in these 2 experiments. So the first part simply asks the student to respond given the retention factors or the distances traveled by dyes A, B, and C, which one's the least polar. The correct answer is dye C, although this is a 2-point question. 1 point for making the correct choice. Dye C traveled the furthest, and the student is prompted to justify in terms of interactions between the dyes and the solvents. So students could talk about dye C is the most highly attracted to that mobile solvent front that is moving up the TLC plate, that non-polar solvent is on the move. Dye C goes up along with it because of that mutual attraction. Or the student can say that dye C is the least attracted to that polar paper. It's on the move, whereas dye B is closer to the bottom because it's more sticky onto that paper. We had a cornucopia of misunderstandings on this particular question. Students would confuse the solvent front with the actual presence of a pool of solvent being at the top of the TLC plate. Sometimes students would say, oh, well, the solvent is down here, so dye B is more attracted to the solvent because the solvent is down at the bottom, so dye B is drawn downwards because that's where the solvent is. We saw a lot of confusion about what distilled down, I guess, to mobile phase versus stationary phase, and what are the mutual attractions between one of the dye molecules and the polar paper versus the non-polar solvent. We saw equal number of answers where dye C is repelled by the paper. So because this paper repels dye C, the paper pushes dye C up as far as it possibly can. This is an example of where students seem to have a lot of experience having done the experiment, but many were not as well equipped to explain the theoretical reasoning why. What's happening to the molecules, what's happening in terms of intermolecular forces, what's happening to cause these retention factors, which, by the way, is not a term that the students was required to use. But why do different dyes rise higher than some other ones? And then the second part of the question is identifying the unknown sample. The temptation was to look at this unknown and kind of draw a line across and say, well, pretty close to the amount risen by dye B. However, it's the proportion between the distance traveled by the dot in proportion to the total distance traveled by the solvent front. Very few students actually use the term retention factor, although many described in words gave a perfectly good explanation that was reminiscent of that concept. If you look carefully, the unknown has a retention factor pretty close to 0.5. The same is true for die A. So the student earned a point for the correct choice, and they earned a second point for a justification based on proportionality, retention factor, some kind of rationale along those lines. It's important to keep in mind that it's not just the height of the spot, it's also the height in proportion or in ratio to the other heights of the other dyes, and also in proportion to the height that the solvent front reached. The advice from the folks of the reading was to give students opportunities to describe in their own words what's going on in chromatography experiments. A lot of it described something that sounded like capillary action. I think the language of mobile phase and stationary phase is often very helpful, but anytime we can get students to not just do the experiment, but to use words in writing or orally about what's happening in terms of intermolecular forces, that's always going to help them to focus in on what they really understand well and what they still need to better articulate. And secondly, in the more along the lines of mechanics of the experiment, it's important for students to know, okay, we look at how far the spots of the dyes rise, but we need to take into account how far the solvent front moves as well, because that's actually pretty important. In a laboratory, we're always careful to mark that with a pencil before the solvent evaporates. The next short question had an average that was closer to 2. This one involves combustion of propyl alcohol. And the students are presented with a situation in a laboratory where they have an alcohol lamp that's burning, and there's a beaker of water suspended over top of that lamp. And they're presented with an initial condition and a final condition, and it looks like the level of the fuel has dropped a little bit in the final. So the student carries out a combustion of 2-propanol in this case, and the student is observing the temperature of the water before and after the experiment. So the students have a table of data here. We have the initial temperature of the water and the final temperature of the water. We have some masses. We have the specific heat of water. Many students were successful in recognizing this question as a calorimetry type experiment and used this particular equation successfully. Some problems, though, are that the mass here is just, well, mass, right? So do we use 0.55 as the mass? Do we use 125 grams as the mass? Do we add those two masses together? A lot of times, what is the object that's actually, or what's the material that's actually getting heated up? It's the mass of what? And in this case, it's the mass of the water that's getting heated up. The mass of the fuel that got combusted down here isn't necessarily reflected in the delta T that's going on there. A lot of students converted degrees Celsius to Kelvin. That was okay, but it was unnecessary. And it's an extra step that gives an opportunity for things to go wrong. So some Murphy's Law there.
Hey, Paul.
Yes.
Quick question. It says, is it expected that students will have experience with an alcohol burner in a high school chemistry lab?
I think very few high school chemistry labs do this anymore. Certainly, I'm not aware of any that I've talked to who actually use an alcohol burning lab. Correspondingly, we use quite a few words in setting up the experiment so that students can clearly understand both in words and graphically what it is that's actually going on. Most folks I talked to said, no, we don't burn alcohol in the lamp. My students, they felt like, oh yeah, you're burning the fuel, and that's generating heat. They understood the experimental setup, even though they hadn't actually operated an alcohol lamp themselves.
Thanks.
You're welcome. So then the student was asked, okay, based on the experimental data, where there was 0.55 grams of fuel combusted, what if 1 mole of fuel was combusted? How much heat in kilojoules would that release? And the student can follow through, okay, if I have 1 mole of fuel at this molar mass, use the proportionality here of how many kilojoules are released on a 0.55 gram scale, so they can scale it up and come up with a Q of combustion. This was the question that requires 2 points, requires the students both to correctly calculate the amount of heat, but then secondly, the student specifically prompted report your answer with the correct number of significant figures. And that's a pretty clear sign, indication to the students that significant figures are always important, but it's especially important in this question here. Students would sometimes try to use the same equation twice to answer this question, Q equals MC delta T, even though it's a different experiment. We're talking about a different amount of fuel that's being combusted, or calculating not the heat exchange for 1 mole of fuel combusted, but 2. And I think a lot of times students would look at this 2 in the stoichiometric coefficient and start with 2 moles here rather than 1. Students would sometimes use 60 for the molar mass, which was okay mathematically. This goes back to an earlier question this evening. 60 is acceptable mathematically. It's very, very close. But the problem is the student would write the number 60 and say, oh, that only has 1 significant figure, right? So they would report their answer then to fewer significant figures than was appropriate. So it's important for students to remember when you're calculating molar mass, this number has more than 1 significant figure.
Okay, Paul, here's a quick question about sig figs. It says, do they allow 1 sig fig leeway, or does it have to be exact?
Let me check my notes. That can vary sometimes. This is question 5, part B. This year it had to be spot on. There are instances in the past where we have sometimes scored exams a little bit more leniently, but that's been in situations where we choose a question out of the free response that we think ought to be the significant figure point, and the students remember specifically cued in. We felt justified in this case because of the prompt saying use the correct number of significant figures. We felt like that 0.55 was straight from the table and was more accessible to the students.
Great, thanks.
You will most often, you will always be welcome. You will always see the significant figure point coming from a laboratory type setting, where there's an actual physical measurement that's related to something that a student was actually able to measure. There's a tip. And then we have a second student performing the experiment, and this student's alcohol burner is contaminated with water. And the student noticed that the difference in mass before and after combustion was the same difference in mass as the first student's. And the question then poses this hypothetical: would the final temperature and the beaker heated by the alcohol burner be higher, lower, or the same as the final temperature as in the first experiment with the justification? So the student here could go down 2 roads. They could say, well, out of that 0.55 grams, there was some water loss along with the fuel loss. So we weren't really combusting a full 0.55 grams of fuel. That 0.55 grams was a combination of fuel lost to combustion in addition to water lost in some way. And usually it's the evaporation, or the water gets heated or whipped up and evaporates in some way. You talked about combustion of water. That was unfortunate. Or they talked about combustion of the contaminated sample. The water was drawn up in the wick, and then the endothermicity of the evaporation or the vaporization of the water caused a little bit less heat to be generated. The students could go down either of those 2 roads and still learn the point. It was interesting that a lot of students talked about the water that was suspended above the burner in the beaker. So when we talk about the water, some students were talking about the water that was the contamination in the fuel. Some were talking about the water that was above, although we really wanted students to focus on the alcohol burner in their responses here. Advice from our readers is helping students to identify in a system what is gaining thermal energy, what part of the system is losing thermal energy, discussing those what-if questions about the actual experimental setup or the outcome, or what if the second student performed this experiment in a different way, what would be different, and how numerically would that impact the outcome of the experiment. And please make sure that students say that we're looking at significant figures that are limited by physical experimental measurements, as opposed to, say, a molar mass or a stoichiometric coefficient. Almost done. Magnesium hydroxide. This was probably the lowest scoring question. Actually, no, on average, this was the lowest scoring question on the exam. Unfortunately, 35% of the students didn't earn any of the 4 points. This is a KSP question that deals with the solubility of magnesium hydroxide. So the first thing that the students are asked to do is calculate how many grams of magnesium hydroxide can dissolve in 100 milliliters of a saturated of a solution. So let's see. There we are. 1 point for calculating the molar solubility. The setup here was critically important because you have to keep in mind all your ones and twos and exponents and coefficients, right? There's one magnesium plus 2 ion corresponding with 2 hydroxide ions, and because of the stoichiometric coefficient, we also need to raise that to the power of 2. So following the math through and coming up with the correct mathematical form was critically important here. So the student could earn 1 point for the molar solubility, and then 1 point based on that molar solubility, calculating the correct mass that could be dissolved. A lot of students, I think, recognize, oh, this is solubility, and they used a mathematical equation that omitted this number 2 and or omitted that number 2 there. It looks like they had memorized an answer to a previous similar question that had a different stoichiometry. It looked like they were reaching for some kind of equation that they remembered back in their memory, but then it was the incorrect equation. We saw a lot of square roots rather than cube roots. You have to follow your exponents through here, and forgetting that factor of 2 is quite common as well. A lot of students said, oh, the KSP has this value, therefore that must be the solubility. Of course, molar solubility has units, and KSP is dimensionless. That's a little bit of a clue that the two are actually talking about different things. And then the students presented with a lattice energy situation, and different textbooks define lattice energy in different ways. So the exam committee went out of the way to define how they were defining it in this case, drawing apart the individual, separating the ions in the gas phase. And the students are presented with a table of data that shows the lattice energy of 2 analogous hydroxide salts, and asked to explain why the lattice energy of magnesium hydroxide is greater than that of strontium hydroxide. And they're asked to specifically use terms of periodic properties and to use Coulomb's law. So what we would like students to say is to compare, well, this is a comparable series. Strontium plus 2 is a larger ion than magnesium plus 2. They don't have to give the reason why in this question, because the question never asked the student specifically why is one bigger than the other. So we awarded the point just for the comparison of sizes, knowing the difference in the sizes of those 2 atoms. When students earned 1 point out of 4 possible, this was the point they earned more often than not. And based on the differences in sizes, then the student needs to invoke Coulombic reasoning, talking about the differences in average distance between the cation and the anion. And they don't have to go so far or to be quite specific as talk about inverse squares, but recognizing that relationship, at least qualitatively, is going to be necessary to earn that second point. A lot of students saw the term periodic properties and started talking about other periodic properties like electronegativity or ionization energy that weren't relevant to this particular situation. They saw periodic properties and just started talking about periodic properties that they knew about. Also, they would talk about the distance not between the cation and the anion, but they would talk about the distance between the magnesium nucleus and outermost electrons, for example, talking within an ion rather than in between ions. We didn't score on this, but it is important to keep in mind that ions and atoms and molecules technically are different things, and it's important for students to keep their vocabulary straight. The advice here, proper terminology, gives us content as readers that we know what the students are that they know what they're talking about and they're describing it well. We think it's important that students not just memorize equations or solve KSP problems based on past memory or, hey, this is the equation that we always use for KSP problems, but actually digging down deeper into the question and actually solving the problem using the stoichiometric coefficients that are actually present in that problem. And then carrying through units, a lot of times we'll see 100 milliliters turn into 100 milliliters turn into 100 liters and so forth. So carrying those units throughout the calculations, making sure that we don't make easy errors like that is always important. And following units from beginning through the middle, all the way to the end, can make that easier. And the more practice students can get applying those periodic properties, describing them, explaining why, choosing the correct periodic trend or property that is sufficient to explain an observation is always going to serve the students well.
Oh, we have a quick question about lattice energy.
Yes.
Is this definition of lattice energy the preferred one for the College Board, or is it the energy released when the solid is formed from gaseous ions also accepted as a definition, referring more to a hypothetical question in the future rather than this question that specifies the definition?
Sure. We recognize, the committee recognizes that there are two different definitions of lattice energy and that different textbooks will use different definitions. So we would never write a question that just flat out asks the student, what is the definition of lattice energy? That would be unreasonable. So what we do then, when we want students to use those kinds of ideas, is we define it in a particular way. I wouldn't say that we have a preferred method. I think in my survey of textbooks, more will describe it in the same way as this question than the other way, but there's a substantial number who do describe it in the opposite way. So we're not expecting students to know magically know which definition we're thinking about. We will always be, and that's why we added another sentence that actually defines, here's what we mean by lattice energy. It adds a little bit more to the reading load on the part of the student, but it clarifies for them exactly what we're talking about. I wouldn't say that we have a preferred definition, but I would say that any time that a term can be defined in different ways, we try to be very careful in being explicit and exact about precisely what we're talking about. Okay, last question. Electrochemistry. The average here was closer to a 2. It wasn't so bad. Students have a situation here where they have two redox equations written out. They have two choices to make in the titration of hydrogen peroxide. And ultimately, the student needs to make a decision about which of these two titrants is going to be better. They get some electrochemical information in the form of half reactions at the bottom. First question asks them to calculate E0 for the reaction between the dichromate ion and hydrogen peroxide. And that is mathematically simple, right? It's arithmetic, one value subtracted from the other, but the kinds of misconceptions that we saw, predictably, students trying to multiply times stoichiometric factors, failing to recognize that E naught cell potential is an intensive property, or some sign errors we saw there as well. It's not always as simple as it looks. And then the second part asks for the E naught for reaction now between the cobalt ion and hydrogen peroxide. Similar setup there, similar kinds of errors and misconceptions. Some of you still out there paying attention might say, hey, aren't these two questions exactly the same? Well, they're similar, they're not identical. The student's going to need this information later on in answering the question. And if the student made the same mistake twice, they were only penalized once. Let's say they had a misconception about sign convention, or a misconception about including reaction stoichiometry in multiplying these standard reduction potentials by the stoichiometric coefficient. If the student made one mistake, they're only penalized once. So a lot of students would earn the second point in this particular question because they're using incorrect reasoning from part A, but they're using it consistently, so they could earn a consistency point here if they're carrying the same error through. Ultimately, though, the student will need both of those values in making a judgment call about which titrant the student is supposed to use for the titration of hydrogen peroxide that they want to do. So, student who got correct answers for A and B, we would like them to see talk about the dichromium ion, talking about how one of these overall reactions has a negative E naught and one of them has a positive E naught, and how does that factor into thermodynamic favorability. Although, once again, for the point of consistency, if students came up with incorrect values of E naught for one or both of those values, we would then look a little bit more deeply into the student's reasoning about, oh, well, both E naughts are negative, but one is more highly negative than the other. Or both E naughts are positive, but one is less positive than the other, talking about those sorts of things. In terms of misconceptions, the E naught for they would use E naughts for half cell reactions rather than looking at the E naught for the overall reaction in its totality. And then lastly, once we have those E naught values, and once we've talked about thermodynamic favorability, then we ask the student to directly calculate the value of delta G naught for the titrant that they chose. Once again, it's possible for students to earn the consistency point here, depending on what happened earlier in the question. That number 6 is critically important, thinking about balancing redox equations and how do we do that, and how do we get the right number there. That's critically important. Students would very often, we see this quite a bit, incorrect conversions between joules and kilojoules, multiplying by 1,000 when they ought to be dividing, or dividing by 100 rather than 1,000. We see that quite often as well. And carrying that negative sign through is important as well in recording that final value. It is part of the equation, and the sign here, when we're talking about thermodynamic favorability, is critically important. So the advice from our leaders and readers has to do with practicing proper terminology, talking about redox reactions, what's oxidized, what's reduced, what's the difference between an E naught for a half reaction versus an E naught for an overall reaction. And then again, having practice students putting those half cell reactions or half reactions, putting them together to describe the totality of a particular reaction and what's the E naught for that overall process. So you do want to reverse the oxidation. For oxidation, you want to reverse the half reaction mathematical line. You don't want to multiply those E naught values by factors of 2 or 3 stoichiometry that are used to balance.
We did have one question on that.
The exam. Very good. Go ahead.
It says, for the questions with choices and justifying the answer, are there instances where students choose the wrong choice but still get a point for the justification?
Yes. We are opposed to the idea of locking a student out of that second point just because they didn't choose the right answer in the first point. There was one on the 2016 exam, I think on question 2, that talked about thermodynamic favorability or a process being driven by delta H not, or delta S not, or both, and that the student had to make a choice and then justify using thermodynamic reasoning. That's the first example that I can think of. But yeah, we don't want to see a student on a 2-point question fail to earn the first point and then have it be impossible for them to earn the second, right? We want to score in such a way that we reward good chemistry whenever we see it, and we want to score in such a way that we're able to differentiate students and use all points of the scoring scale. If we're only using 0s and 2s and none of the 1s, we're not differentiating as well.
Great, thank you.
You're welcome. That takes us to the end. I feel like I just took an AP chemistry exam. Here are some big pictures. Big picture advice from the readers as a summary about the importance of reading the question thoroughly, following directions, and staying on point. It rarely, if ever, is necessary for a student to rephrase the question or to write a mini essay on any question. Lengthy answers usually are not going to be any better than a short answer that's right on point. Strong skills in argumentation, claims and evidence, vocabulary, terminology. Please minimize use of pronouns. I never quite understand what it or this always refers to, and it can sometimes be very confusing for the reader and hard to parse out. There's still plenty of math in the AP chemistry exam. It is alive and well, so those skills and quantitative reasoning, using units, symbolic rearrangement of algebra can always be helpful. Those lab skills can involve not just the mechanical act of doing the experiment, but thinking about what's happening to the molecules, what's happening to the atoms or the ions at various points along the way. Thinking about chromatography, for example. Error analysis, and thinking about what changes and how does that impact the outcome of the experiment. And finally, that importance of communication verbally, mathematically, as well as graphically, and especially particulate representations. I owe a lot of gratitude to the leadership who were present at the reading, the whole chemistry team who helps us at ETS and Test Development Committee. Nobody does this alone. Serena McGrogan from the College Board has been fantastic to read with, and there are some awesome readers and leaders who contribute a lot to this process. So there's one more slide after this for the survey, but I want to make sure I park here ever so briefly. If you want to send me an email or ask follow-up questions or get a copy of it.
All right, so technically he's done going over the test, and there's a short little time period here where if this was actually done on a webinar, which is basically, for those of you who have never heard of a webinar, it's basically kind of like all of this was done live online and people logged on to a particular thing to watch it. So it was like a really big group Skype call with a PowerPoint presentation and someone talking about it. Okay, so they have a quick survey for everyone who's logged on for them to say, how did it help, blah, 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 blah. As soon as that part is over, everybody that was logged on can have a chance to sit there and do a Q&A with the reader. So there is a little bit more for anyone who wants to go on, and it will kind of tie in some specific questions from chem teachers. Well, hey, what if my student does this? It's not specifically necessarily about a question, but there's only about 20 minutes left on the video, so part of that is the survey time, but just kind of giving you an idea if some of you want to stay. And I'm going to kind of get through
Interesting. I happen to be chair of the chemistry department here. It is a question that we ask, but I'm not aware of any formalized mechanism nationwide where students are asked to do that. AP credit policies are usually determined at the institutional and or departmental level. A lot of times when I'm trying to decide if a student is more appropriately placed in General Chemistry 1, General Chemistry 2, on rare occasions even directly into sophomore organic. The lab experience does come up quite a bit. I've had students actually bring me their lab notebooks or descriptions of experiments and talk to me a little bit about there. Intellectually, the students are usually ready for the higher level work, but the greatest variation that we see in terms of student preparedness is in the laboratory.
All right, so, and when does that do?
Great. And then there's one more, and then I think we're going to call it a night. It's a nice one. It says, what's the best way that we as teachers can prepare for teaching AP chemistry?
Funny you would ask. I have a daughter who's taking
Check one, if you're in the building, please report to the main office.
course right now.
Check one, if you're in the building,
I think
please report to the main office.
So that's the end of it.
Other than questions from the teachers that may, some of it may be beneficial, but yeah.
Okay.
Symmetric. Certainly. I think students need to see looks like. There's a particular style to the multiple choice questions and pre-response. Hopefully with some insight about how that's scored. I know some teachers will even simulate an AP chemistry exam or score their exams on, using a scoring rubric. I think that the more experience the students get, first on the fundamentals, and really just understanding chemistry. I think, like a question like what makes a good teacher? It's hard to define, but I know it when I see it. I think that every student is different, every school is different, we all have different students in our classes, different resources. We have to find what makes it work to be an effective teacher. So because the students are taking a high stakes exam and it's a national curriculum, every student will be taking the exam, preparing along the way. I think maybe the most important, most helpful thing to do
They
is to
started
take
going
time out
on
every
a
now and again
discussion about what electronegativity
show
was.
students
There's no reason.
choice questions.
You're wanting to know
the free
how long of attraction and distance. That was it. There's no reason to talk about the fact that strontium and magnesium have different electronegativity. That's nothing about what's question on. Answer the question that's asked, not the one you wish was asked.
I can talk about this.
Okay. All right. So, hey.
Great, thank you.
All right.
That's about all
So,
the time we have. Thanks again, Paul, for a great presentation.
That's it?
And thank you all for being a great audience.
Thank you, Cindy.
Yes, thanks, they were great.
all right. Well, we couldn't hear everybody talking in here anyway. Let's be honest now, and this isn't me just being snide, but if it's not your question, it's not an important one. I know I'm not wrong, but that's the thing right there. They were teachers asking the head reader of the exam questions that you might have needed to know when we were all talking over it. Because it wasn't your question, it wasn't important at the moment. Okay, so, as he was going through this, so many things over and over and over and over, I'm like sitting there back in the back, tally marks. Yes, I said that a billion times, I've said that a billion times, I've said that a billion times. Every single one of those big points, you have heard me say at least 100 times since August. Show your work. Units throughout. Answer the question that was asked, not one that you wish was asked. Sometimes less is more. Don't write a big long dissertation. Get to the answer first, then your justification. You heard him say that so many people, on one particular problem, students jumped right into calculations and they never got around to answering the question. Well, I've got a whole bunch of pre-AP tests that did the same thing that I've kind of said over and over and over. So most of those tips and things he said about it are nothing new to you, but I do like the fact that you were hearing it from somebody who's not up in the front of your class and who is responsible for putting your grades into the grade book. Because all too often students think, oh, well, that's just Mr. Cousins being a jerk, or that's Mr. Cousins being hard. It's not actually going to be that bad. Yes, it is. It's not just Mr. Cousins. That was one of the people who actually writes the AP test that you're going to take in 12 days. So take his word for it a whole lot more than you'll take mine. I don't write a bit of them. And I have never graded one. I still have one more year before I'm eligible to go be a reader.
How many years?
You have to do 3. But I do plan on being one at some point. Because
it's a just like a one.
It's a what?
It's not like a permanent thing.
No. I mean, it's you guys take your exam May 7th. The makeup exam is May 23rd. All of those exams get sent to one location. And you saw, well, for those of you who were here at the very beginning, did you pay attention to that slide? That was
anxiety.
Well, and that was a
description.
where was it at?
Thank you as well to the.
No, you cannot view this because you are not a member of American Association of Chemistry Teachers. So
It'll
I
be on
cannot
my
post this
YouTube channel. It'll be on my YouTube channel.
I took all these photos in public too.
You wouldn't be able to get to it. You don't have a username and a password. Well, so it would be a link, and it would ask you, prompt you for a username and a password, and you would sit there and stare at a blank screen. Yeah, it's so. I could post a link, but the link's not going to do
So
you
yes or no?
a bit of
Josh,
good.
yes or no?
Where is that?
I'm not asking. I'm not making a joke. I'm asking a question.
I was about to show you that just one more time, that picture that. No.
Am I driving your car? Is your job going to school so you can drive your car? That takes a lot of hours.
I don't like driving your car.
She needs.
You like slide through the windshield.
He even tries to do a meme. Did you see it?
Oh, can you sign my name?
You got my seat.
Yeah, try with your ears in.
Your mom's in a pickle jar. Don't call me stupid.
She's
It's not a YouTube video.
and Mama is crazy. Oh, I love my name. Oh my gosh, you know how to spell names?
Oh god.
Oh, you should have done a roll card. Darby's a roll card.
I don't know. Okay, so, alright. So, I hope this kind of helped you quite a bit. The more you wrote down as far as those common errors and misconceptions, probably the more you would have gotten out of this. But obviously that set of scoring guidelines is yours to keep. But, hey, ladies, gentlemen, just like those notes that some of you got that you never once looked back at, this really only helps if you go back and look at it again. Now granted, if you're still here at 5:27 on a Wednesday evening now, you are probably not the ones that I'm referring to about the notes, but you know what I mean. You definitely know you have some classmates whose notes still almost look exactly the same as when I gave them to them. Alright? But the more you practice this stuff, the more you see actual AP problems, and the more you go back and practice them and try to do them on your own, the better you're going to be. So, you have the whole set of scoring guidelines to this. You can also just, quite simply, just in Google, 2017 AP Chem FRQ, hit enter, and it will bring the first 2 links. The very first one is going to be that scoring guideline. Okay, yeah, here's the room right there. Those are all the AP exams.
Oh my goodness. God bless them.
Oh, those are boxes?
Those are boxes. So, hey, hold on, let's hear me real quick. So when I am talking about at the end of the day, and the reader is grading yours at 5:29 p.m., and they have been going through this all day, you can imagine that their attention span and their focus might not be as sharp as it was at 8:20 in the morning. So that is why I am saying two things he didn't talk about. One is penmanship. Here's a very, very simple thing. If they can't read it, it's wrong. Yeah, Austin Wynn, for those of you who know him. I goose him on this every time I see him because he knew his chemistry. He got a 2 because they couldn't read a damn thing he wrote. And that went double for me because, yeah, I never, and you can ask Waxell, he gives him 0s on FRQs as well because he can't read them. Look at that. If you can't read somebody's, are you going to sit there, if you have that many staring you in the face, are you going to sit there and try to discern, does that say the, or does that say cat? Does that say she? No. If you can't read it, it's wrong, they're going to go on. Okay? So, but on, back to what I was saying before we saw the picture, if you just Google the 2017 FRQ, try working some of those out. You have the scoring guidelines, and after you have worked out, do them like one at a time. Don't sit down and do a whole hour and 45-minute long test. But do one question. Then look at the scoring guidelines, and if you wrote down what those misconceptions were, sit there and look, oh crap, I just made one of those misconceptions, or one of those things, those errors that students made all the time. And figure out what it was, how to avoid it, and then the key is, don't do it again. Alright? So, tomorrow after school, it's going to be a short one because I am leaving before now. I will be leaving at 5:15, and if you're not done, I'm kicking you out the room and locking the door behind you.
Oh.
Yeah, it's very important. But we'll be going over gas laws tomorrow, but in class we're going to be doing thermochem FRQs. Okay, so those of you who were here yesterday when we went over thermochem, we'll see how well you picked up on that. All right. Everybody, thank you for coming in, and I will see you all tomorrow.
You're welcome.
All right.
Yes or